particle physicists for the last 50 years or more proceeded by every time a new phenomenon was discovered, they added a new field or particle. Right? So there was electrons and protons were known, and then they couldn't really understand the structure of the nucleon, so they added quarks, and then there were gluons, and that all worked very well, but then new accelerators came along, they found new particles, they kept adding more generations of fermions. So basically, the mode of operation of the field was you build a bigger accelerator, discover a new particle, add some more stuff to the standard model. That stopped working around 1980, essentially in the 70s. The current framework of the standard model was all in place, and no accelerator since that time has discovered anything extra, right? So all the major theoretical ideas were in place in the late 70s. And so far, the bigger accelerators we've built, we've not found any new particles that weren't already predicted. And so this is kind of shocking. The Large Hadron Collider, was built to find the Higgs boson. It did, but that was predicted in the 60s. Most theorists were predicting there would be a slew of new particles, right? Instead, we find nothing. And so I am very interested in the idea that perhaps we do know all the laws of physics. They're sitting in front of us. We've got Einstein's theory of gravity. We've got the standard model. The challenge for cosmology is understanding how these things work together. It's not so much adding new ingredients. I believe it may be true that we don't need any new ingredients. All we need is to understand how the ingredients we already know fit together. So my philosophy has become one of extreme minimalism.
Right.
Let's try to explain everything we see with the minimum number of theoretical principles.
Now, what's interesting is that this is a hallmark of simplicity and beauty. And physicists, as well as mathematicians, but physicists are motivated by, in large part, beauty and simplicity. So why is this such a controversial view?
It's a good question. I think, frankly, it's people got into bad habits.
Such as? Not which people, although you can talk about that, but the bad habits in particular.
All the people like me, okay? Everyone like me. And I was in these bad habits too. I entered the field in the early 80s, where the standard model was in place, and people invented the idea of a grand unified theory. Okay, so grand unified theory was supposed to unify all the forces, strong, weak, and electromagnetic forces, unify all the particles, electrons, quarks, neutrinos, and so on. But the idea was the way you unify them is by putting them all into a bigger framework called the grand unified theory. So the hope was that you would get a greater degree of simplicity and beauty by adding more stuff. All right. So as well as the forces we already know, there would be other forces. I mean, in the standard model, in a certain sense, there are 12 force-carrying particles. There are 8 gluons, 3 weak bosons, and 1 photon. Okay, so 12 force-carrying particles. In the simplest grand unified theory called SU5, there were 24. So you added 12 more, okay, in the hope that the complicated group structure of the standard model, which is SU3 times SU2 times U1, that would all be included in SU5, okay, which sounds simpler and more beautiful, more elegant.
Right.
But the way in which this was done was extremely naive. It was to say, look, we know a certain number of the ingredients. Let's imagine that there are more particles which are heavier and so haven't been found in accelerators. When we add in those more additional particles, everything will simplify and become more beautiful. It never really worked, because when you added more of these force-carrying particles, you also had to add more of another kind of particle called a Higgs boson, which breaks the symmetry, which would break the symmetry from SU5 to SU3 times SU2 times U1. So you kind of unified it in a sense, but then you had to add more stuff with more parameters and more arbitrariness in order to sort of unbreak or to break that unifying symmetry. So, and then people went further. They said, well, maybe SU5 isn't the whole story. So, let's add strings.
Mm-hmm. Right.
So now you had strings with all kinds of extra particles, in fact, infinity of extra particles. And then string theory didn't work, so in 4 dimensions, so you add 6 extra dimensions of space. And then string theory didn't really work. There were too many string theories. So then people came up with M theory, which is now 7 dimensions of space and has membranes in it as well as strings. And this sort of just kept escalating.
Editor's note here, superstring theory has 9 plus 1 dimensions, so 9 dimensions of space, 1 dimension of time, and M theory has 10 dimensions of space and 1 dimension of time, so 11 dimensions in total. There's a string theory iceberg video where I break down the math of string theory in 3 hours, and the link is in the description.
Correct, yeah. So M theory, you added another dimension, but it's a bit of a peculiar dimension, which has strange ends to it. So yeah, initially I was very taken with all these ideas and I pursued them very vigorously. What has always distinguished me from other cosmologists, I think, is my focus on observational tests. I think all of these theories are nothing unless they make clear predictions.
Right.
And we tried to use M theory to explain the Big Bang itself, and then to get predictions. And we kind of showed that in a similar manner to inflation, we could fit what we see in the sky. But, the number of parameters in the theory was way in excess of the number of observable parameters. And so I was never very happy with that. It's not a real theory. It's not really predicting anything. It's only fitting things. So I've become much more demanding. I want a theory in which we take the forces and particles we know, and we don't add anything else, and we nevertheless explain how the Big Bang worked and how quantum gravity works within this minimal framework. This is, if you like, the extreme optimist view, that I think maybe we've discovered all the particles we're ever going to discover. Or almost all of them. And the real task is figuring out how they work together consistently. Now, why am I optimistic? I'm optimistic because of this point of view. One, the Large Hadron Collider hasn't seen anything else, so that confirms this point of view. Secondly, observations of the cosmos are pointing to extreme minimalism. Right? So if you ask, how many numbers do I need to describe all cosmological phenomena on large scales, right? How many parameters do I have to add to the standard model? And the answer is 5, just 5 numbers. And they're all very fundamental numbers. So one is the cosmological constant, sometimes called the dark energy. This is a very, very basic number telling you how much energy is in empty space. 2 is the amount of dark matter compared to ordinary matter. Again, a very fundamental number. 3 is the number of baryons, which are protons and neutrons, the nuclear particles we're made of, compared to the number of photons. Again, a very fundamental number in physics. So there are 3 numbers for the matter content of the universe, and then just 2 numbers that describe the fluctuations we see in the universe. So what came out of the Big Bang wasn't perfectly uniform. It has some slight density variations from place to place, And those gave rise to galaxies and stars and all the interesting structure. So the amazing thing is today, by looking back to the early universe and mapping the cosmic microwave background, we can see these fluctuations and measure their statistical properties. And they turn out to be unbelievably simple. It's basically what's called Gaussian random noise. It's the simplest possible random noise pattern you can imagine, with a scale invariant spectrum, meaning that the variations have the same strength on all scales. And so that's one parameter, the strength of these fluctuations. It's about 1 part in 10,000.
Mm-hmm.
And secondly, there's a slight tilt, what we call a spectral tilt, that the fluctuations get ever so slightly stronger on large scales.
So it's not exactly a scale invariance, it's just close to it?
It's not exactly. It's scale invariant with the tilt of 4%. Okay. So if I go, if I change the scale, what's the way to say it? Basically it's saying that if I,
if you have waves of a certain frequency, that they're more diverse or more varied than the others?
The longer wavelength waves are ever so slightly stronger, but only by 4%. So if I, so basically if I double the wavelength, then the amplitude, it's actually the power spectrum, so it's the amplitude squared, goes up by 2 to the power 0.04. That's 4%.
Right. Okay.
Now it's a very, very tiny amount, but it's also a very beautiful thing that it seems to be a perfect power law over all the scales we can see. It's what's called, in physics, we see this in more mundane phenomena, it's called a critical exponent. And it looks like that's what the universe has. It has scale invariant power spectrum with a small critical exponent. So basically there are 2 extra numbers. So altogether you get 5 numbers specifying everything about the universe on large scales. Now, the simplest inflation model would add a whole slew more numbers, on top of these 5. And enable you to fit them, but you're not really explaining them. What we've been able to do is explain all of these 5 numbers without introducing any new particles or forces into the standard model of physics that we know. So it's an extremely minimalist program.
If you enjoyed this toe clipping, then the full video is linked in the description. You should also sign up for toe mail, which is again in the description and the pinned comment. You'll receive immediate access to all exclusive updates from the Theories of Everything podcast. It also helps me communicate directly with the core toe community. You'll also receive my top 10 toes. Think of it as the intellectual version of Quentin Tarantino's Obsession.